So, starting off, I guess, with CAD, it's important to think about perspectives in CAD. So when you look at this, it looks pretty normal. As you're looking down these train tracks, something you can notice. The train tracks are getting closer and closer together, closer to the horizon. Things in the background, like the fence, or not fence posts, but the power lines are all the same height. We know they're all the same height, but they look like they get smaller and smaller and smaller, closer to the horizon. Same with the railroad tracks. We know the railroad tracks are perfectly straight, but at a distance they converge. If you were to measure this with this kind of perspective, you'd measure where you are, but if you try to measure further apart, it might be more difficult because things are converging. So this is called the vanishing point, where things disappear, or onto the horizon line for things that are a bit further out in your perspective. And that decrease in size is known as parallax. And another thing is parallax motion, where things in the background will move slower than things that are much closer to you. If you're moving, or if you're driving by a mountain really far away, it won't move nearly as fast. And in the 3D world, it works great. In 2D on a screen, not so much. It doesn't really translate as well. And in 3D, your mind can make sense of like, okay, well, things that are smaller far away, things that are close are big. But on a screen, which is just flat, and you have a small thing and a big thing, there's no telling how far away they are, really, because you don't have anything to reference on. It's just a screen. And it doesn't really work. So if one vanishing point doesn't work, maybe we can go to more. There's 2, and there's 3. They look distorted just like by looking at them, so I don't think it's going in the right direction. Let's try something really out there. Let's try 5. No, that doesn't look good at all. Guesses for how many vanishing points are in this photo? I see 1. So when you're looking at the vanishing points, you can think from the 2 examples, maybe you're between 5 and 1. In the 5 example, as things get closer to their vanishing points, at the poles and around the sides, things start to bend. But in 1 vanishing point, things are going straight until they reach it. And so in this first picture, if you look at the buildings, all those buildings' corners are all straight, or edges, I should say, are all straight, and they all point into the middle. So we know that there's at least 1 vanishing point in the middle. But as we follow the building, those buildings don't curve like they would in 5 or 2 or 3, which means there's no vanishing points on the outside of that picture. So there's only 1. That's 1 vanishing point. So again, this is a fisheye, 1 vanishing point view of how we see the world. As an exercise, it's super simple to kind of show it to people. I think I might have got it across already, but in case you haven't seen it. On the roof, there's a lot of planks. All of them are the same size. They're all perfectly straight. The one above you looks big, and as you go to the back of the room, they look smaller, more compressed. In fact, if you're standing from where I'm standing, it looks like the room is kind of diving inward. From my perspective, there's a horizon somewhere in this room, and all these lines converge to a vanishing point somewhere beyond the room. To make it work on a 2D screen, if we were to rotate around that room, imagine the dimensions shifting and compressing and expanding as we rotate around. It looks weird, and when you are trying to get precise measurements for objects that you're designing, it's tough to say, okay, what is straight, what's not. I know that these walls are perpendicular to the ceiling. I know that the walls are parallel to each other, but when I look at it, I see this. When I'm in CAD, I want everything to be as straight as possible so that I know when I look at it in first glance, no matter what perspective, that these are parallel, and if it's off by any bit, then I know there's an angle between those parts, or between those planes, or otherwise. If it's on a ceiling, I don't want to have any kind of angles between them. That you'd have a perspective, I want them to be perfectly perpendicular at all perspectives. So if going to more vanishing points made it look much more cockeyed, doesn't really work. What if we go to no vanishing points? If the fisheye lens looks super distorted with all the light coming from different directions, our eyes look slightly better, being not so distorted. If we made that lens completely flat, would it look any better? And that's what this is. So all CAD, it's called isometric. or the isometric view, iso meaning equal, metric meaning measurement. And so the top one is an example of an isometric drawing where in CAD there's no vanishing points. Those lines will continue infinitely in their direction. They will never converge. They'll never diverge. They will always go into the direction that they're going. If you're in perspective, you can see that the lines aren't perfectly parallel to each other. We know that they are, because mentally that's how we've seen the world for a long time, but we know that there's at least a vanishing point that goes down. It looks like there's probably a vanishing point over here and one over here. So that's 3 vanishing points. If we rotate that, those angles shift as we move that part. And it's difficult to say what is parallel, what's not, what if it's on a slight angle. Where in isometric drawing or an isometric view of things, there's no room for error in that regard. It's going to be perfectly parallel, perfectly perpendicular. So there's a failure with isometric drawings though. On your model, it won't always be shaded. With this I can tell, okay, there's light coming in from the top. In CAD, there's no light or no source. It's all bright, I guess. And so you lose that sense of direction and you can't tell what you're looking at. And so what happens if you use just isometric drawings when you submit parts for manufacturing, it looks like this. It will have some kind of, what's the word I'm looking for? Optical illusion. It could be convex, it could be concave. You're not sure if that cube is actually a cube or if that cube is 3 planes that are kind of meshed together, or not meshed together, but up against each other. And so to get around this issue, we use what's called an orthographic view or drawings on our drawings. So what orthographic looks like is this. And so with that, all your models are going to be isometric, but all your drawings will have orthogonal or orthographic views to them. In your drawings, the orthogonal view, or if you were looking at isometric, instead of looking at it from a corner, if you're looking at it from one plane or another, if you've all done this before with your X, Y, and Z plane, if you're looking at an isometric, it's like this. Orthogonal is the 3 directions that you would look at it like this. So I have an example of one I did last year. This is a bolted connection for members of the chassis, where the chassis tubes would be disconnected, taken off. And this guy would kind of bolt things together. So over here is the isometric view, and then these would be the orthogonal views. This one being the top, where you see the bolt holes are far apart. You have the right side where they're close, and then the front view where it's head on to the square tube. So I'm going to use this train track example. If in this picture you're looking kind of down into the train tracks and forward, if we went level with the train tracks, so the train tracks start like here, they kind of come in and they converge like that, I guess, down to the horizon. You still have your power lines that kind of disappear into the horizon as well, but now you're like laying in the train tracks. An example of it in NX, if I just go down here and pull it up, if you remember that train image where we had horizon, you had like a pole here, and the pole gets smaller as you go closer, and there's train tracks like that. They're kind of leading up to it. This is the same thing in NX. So instead of the tracks converging in the like further away, also I guess in this perspective we're a little bit higher. In this perspective, you can't tell how long they are. You can't tell how far those trees are along the tracks because everything is equal height. So these trees are the same height. We don't know how far into the page they are or into the screen until we rotate it and we find out that it's actually very, very far. But you wouldn't know that unless you rotate it. So that's what isometric is. So these trees are the same height, but they're different distance, and so the further away they get, they don't shrink, they stay the same height no matter what. And when we rotate it, we can see that they're not close at all. So if I just go snap it to isometric, this is what the isometric view would look like. We have straight up, and we have your X and Y plane coming out, or I guess it'd be down this way. There's what is it, 120 degrees, I think, and between all three of them for isometric. I see nodding, I think that's what it is. And you can snap to the different planes. So from directly above, it looks perfectly straight up and down. From the right side, oops, it's perfectly straight. And then from the front, it is straight. So there's also, I should say, when you're doing stuff in CAD, everything is made of simple shapes. So no matter what you look at, when you're designing something, your computer will always have to break it down to these simple things, either a combination of them or a subtraction of them. So take a block with a bolt hole in it. That would be made from A, cube, but you subtract C, a cylinder through it. Simple enough. If you had a cube with a party hat, it would be A with D on top of it. And that's how your computer thinks about all your modeling. And that's how it makes things. When it gets complicated, it just gets smaller and smaller and smaller, and several of them, and it strings them together to make whatever shape you're looking at. But this is generally what you'd be looking at. So in your CAD environment, there's three main ways to actually take a look at your CAD. There's a few others, but no one cares about them. So you have line, which is also called wireframe. You have a surface model, a solid model, also called volume, also called body. I'll start with the solid model. The solid model is how you perceive parts in the real world, and when you take a segment of it, like in the top right, it's filled. Its volume is filled. For CAD purposes, if you're modeling something, you cut it in half, you're like, oh yeah, it's full, it's great, I love it. Your CAD is screaming because there's so much information packed into all those points that fill a void. When it's calculating, it's thinking, okay, I have this outer surface and everything inside of it is filled, and it allows you to do some kind of math stuff. But it doesn't need to be like that. When you export that file, it's going to have a lot of information that you could cut out, because all you really need is the surface. And so that's where the top middle one comes in. It's just the surface. So the surface models are infinitely thin, and they just show the outer boundaries, I guess, of your part. Technically, this could also be a surface model, you just don't know because it's not cut in half. Video games use surface models a lot. If you ever rotate the camera and it clips through something, because volumes are extremely resource intensive, and it's much easier to just make a surface with a picture on it. So when you're modeling stuff in CAD, it's going to be a surface model, but it's going to try and trick you that it's a solid, but it's going to be a surface model. I'll get to that guy in a second. That's also a surface model. But the last one is the wireframe. So wireframes are like that, very, very simple, used in building and construction stuff a lot, floor plans. So if you're in civil, you're going to be doing a lot of that in AutoCAD or Inventor Studio. What wireframes are good for people that aren't in civil or mechanicals, which I'm guessing a majority of you usually are, it allows you to kind of have X-ray vision through your part, so you can say, oh, from looking at these ones, I can only make 3 bolt holes on that base plate, but when I turn the wireframe on, I know there's a 4th one behind that center tube thing. It also gives you information about how deep things are and where they are, and it's nice if you have a lot of components that are all built together and things are meshing weirdly, or there's a lot of complex stuff going on. You can turn the wireframe on and say, okay, I know that this face does touch some internal thing that I can't zoom into because it's hidden. So wireframes are good for that. So back to this complex surface, if you're in aero or the aerodynamics sub-team, you're going to be using a lot of complex surfaces. All their wing profiles and such are complex. If they have side pods like Mark IV were very complex. It uses the surface. So a big issue with, or not an issue, but a reason why they would use a surface over a wireframe or a solid. Imagine this in a wireframe. I can't. It would look super weird. What, you have to have like lines going all over it, I guess, but then lines denote edges, so like where do you put the edge, the smooth object? It wouldn't work. Solids, how many of you have taken calculus? Okay, so you know that integral under the line of an integral is the area or whatever. It takes a lot of computation to do it, and it's not an exact, well, it's an exact approximation. I know, it's weird. You'll get into it, but for volumes, it gets really complex, and your computer doesn't want to deal with that. It would prefer a shape like this, where it's just a surface and doesn't have to calculate all that volume underneath of it, because it's nasty. But in real life, that wouldn't be a surface. It's going to be a solid. It's going to be the handle to something. It's going to be whatever that would be. So when manufacturing, an example of this, going back to aero, is their toolings. So in order to make the shapes that we do, we start off with, I'll just say, like a big block of wood. And we carve it down to that shape, and then we just take the carbon fiber mat or the carbon fiber sheet, we just kind of drape it over it, and it assumes that shape. So that is the sheet of carbon fiber that's just kind of rested over this big block of wood. But how do you get that block of wood? So you can use a machine or a CNC router to make that shape using a program that goes down. And like 3D printing, where you're starting from the bottom up and you're adding, a router is subtractive, where you take a big block of something and start cutting it out. So you do a really big one at the top, and you start going down, and you go down, and you go down, and you go down, and you go down. And eventually you have a shape like that. It's not going to look just like that, because unfortunately, as you start shaving off layers, your machine has to take steps going down. So you get this kind of terraced look. There's 3 ways that we can deal with this, which if you take calculus, you'll recognize these. You can approximate it by going over, even, or you can approximate the curve by going under. So if this is going to be the final shape that we want, and these are going to be what the slices we take out of this piece of wood, which is the final shape that we want? Do we want to have the final block be less than the actual curve, about equal to, or more than? Which one do we want? More. So after we cut off all this extra material, and we have these steps where there's more material here that needs to be removed. What we do afterwards is we have this rough looking thing, looks like Minecraft almost, and you can take a sander to it or a chisel, and you start buzzing it down so that eventually you get this smooth shape. You can't tell if you've taken off too much or anything, so if you get ripples in it, it's kind of up to your discretion to understand that, hey, if I start taking off the edge, as soon as this point disappears, I'm at the limit. I can't sand anymore. If I sand anymore, I'm actually going past the surface. What we used to do, the first time we tried to do a tooling like that, or a big block for composite stuff, we did even, because that's what it defaults to, I think. And it didn't work at all, because now we had space in here that we need to fill, had to remove. So botch that one. Tried it again, reset it. It was under. And the idea was, all right, I know that these edges are the ideal, and so I'm going to fill this space, and then I'll know that I have the true edge, a true corner, and then everything in between will be like stuck full of stuff. And so we used glue, and we just poured it over this shape, and so that it filled all those crevices. And then afterwards, we take a sander to it and make sure that it was smoothed over, and you just have the edges. It didn't work at all. It was super nasty to deal with. We botched that one too, went with this one, it worked great. We're going to be doing that from now on. But it's an example of something like this, where it's super difficult, and if you're trying to measure from point A to point B where you don't have any kind of reference, like a part that has flat edges. It needs to be a surface. A really, really big thing, and I'm not going to get into tolerances, which is different, but dimensions. So 2 big dimensions, I guess, or 2 things I should mention. I think you were telling me to do this. Huh?
2 major dimensions?
2 major dimensions. So you have driving dimensions and you have driven dimensions. So driving dimensions, if I define it, and for example, so like this gray one, this 30, this is a driven, but all the black dimensions are driving. So when I define it, I say 100 is the driving dimension, that line will be 100, and things based off of it will know that that line is absolute, it is a driving dimension, it is how I'm going to define my model. A driven dimension is a dimension which is true. You don't necessarily need to do this, but it is correct because the other ones are correct. So if we look at it, so that one which is 30 and this one which is 50 and 20, they're all vertical. It looks like if I define this shape, I define 50 first, or no, how about this? I start at the origin, this red line here, say X and Y. I drew a line. I made it 100. It is absolute. From its end, I drew a line. It is 50. It is absolute. I drew a line. It's 30. It's absolute. Because this is all defined so far. 20 absolute. 70 absolute. And I connect the end. I don't need to say that this is 30 because mathematically I know that I went up 50, down 20, and now I'm going down whatever's left. It knows that it's 30. It is a driven dimension. Now, when you're editing a shape like this, you wouldn't edit your driven dimension, you'd edit your driving dimensions. If I want to make it shorter, I'd say instead of making it 50, I want to make it 40. The 20 is a driving dimension. It doesn't change. It's absolute. So it gets shifted down. And this one is the one that would change. The 30 would decrease. I made that in NX to just kind of show it. Right here, let's go into it. So this is what, oops, sorry. On the presentation, that's what it looks like in SOLIDWORKS. This is what it looks like in NX. The origin now is that blue plus sign. And you can see the dotted lines being your axes, which in this case are X and Z. So we're looking at it from the front view because Z is vertical. If I change 50 to 40, you'll see that this 20 stays the same, and this 30 should decrease to 20 because it's a driven dimension. And I make it back up to 50, it's driven. If I change this one to 30, then the 30 in brackets, the driven dimension should change to 20. Pretty straightforward. Something that was wrong, I guess, or different in NX, which was on the SOLIDWORKS one. On the SOLIDWORKS one, the 100, the 70, and the 30 were all driving dimensions. In NX, I should know that after I go 100 this way, 30 this way, this last one that hits back up with the axes should be 70. That should be, if I'm going like this when I'm making it, that 70 should be a driven. So if it's driving, and this is driving, and all three of these are driving, what happens if I change one of them? If I change this to 90, what do you guys think is going to happen? Error? Okay, what do you think is going to happen? It's going to compress one of the driving ones. Okay, any other suggestions? So in NX, instead of the dimensions being driven or driving, the lines themselves are. And so when I submit this, it breaks the shape from what it was supposed to be. It's supposed to be an L, now it's broken. It's still 30 tall because these two driving dimensions haven't changed. These also haven't changed, and so the only thing that can give is the one thing that was driven, which is that last one, and so it has to bend out of the way. This happens even if, and under under SolidWorks, you can say, I want a line to be horizontal, I want it to be perpendicular, I want things to be collinear. So you got two lines like this, parallel like that, right? Perpendicular, it's all up here. Tangent button, if they should be in equal length, yada yada. Those will break because those are driven. The driving dimensions will break the driven dimensions if you edit them. So just keep in mind where you're putting dimensions, and you shouldn't dimension your entire part because when you try to change one of them, you'll probably break something. So something better, if I was doing this, it's a very slight change. Maybe you noticed it. When you have a fully defined line or part, it will be black. So this line, which is 100, is black because I know that it is fully defined. If it's not fully defined, it's an orange color. It's much easier to see on a screen than it is on projection. But if it's not defined, it's orange. This line and this line is defined, but I can drag it now. I can drag it up and down because that 50 isn't. I can't drag it side to side because 100 minus 30 is still 70. This guy is still, it's set length, but it is highlighted in orange because it can change position. It can translate up and down. I changed this back to 50. And I got rid of something like this guy. This loop here is fully defined in black because from the origin, 100 over, 50 up, and 30 back is fully defined. But this line isn't anymore. But it's still defined this way. But it isn't defined like this anymore. There's nothing to say how high it is from the origin. Nothing, oh, I broke it. Nothing to say how high it is from this line either. As a rule of thumb, which I like to do a lot when I'm modeling stuff, instead of dimension the line itself as whatever it is, I'll dimension it from an axis. It's just more absolute this way, making it from the origin coming up. You can make it so that an individual line is referenced to itself, basically, but if you have something really complex, it might get difficult. You might want to go to something like this, where everything is based off of a single point. In manufacturing, this is good because imagine you had one true edge or one true corner, and you know that everything from this edge outward is where I want to be. And you start machining things and you start taking metal off, but you know that this corner is going to stay the same no matter what. That is what drawing up dimensions from an origin is. If I said, okay, I want you to machine 100 this way, 50 this way, and then 30 over here, that 30 is still a dimension, and on a model it's correct. Rather, from doing this, I'd say from the origin, go 70 over and start your cut. That way, the same point is always in reference, and when you have it on a mill or something, you can go from there and you start making your part. Where if you had to make cuts in sequence, that line is now in reference, and you have to make the other ones first, which isn't always advantageous. Sometimes you want to start with the 30, but you can't because you're reliant on the other parts before it. In this case, it's super simple. You could probably get away with it. More complex models that you might be making, you won't be able to get away with it. You'll have to start from an origin. What if I didn't declare this, if I just left it blank? Do I need this? Looks like I do. I don't think I need it there. If I know that I go up 50, I go down 30, go down 20, that last line is going to be 30, unless I said otherwise. from looking at this, I can assume, because I'm looking at it in orthographic view or from like one plane, that the line which is 70 long is going to be perfectly horizontal. And as such, there shouldn't be a change. If I said there was a change, then I know that that line isn't actually perfectly horizontal. Okay, so if I can get rid of that one, how many more of these do you think I can get away with? Well, I probably don't need one of these guys. Oh, look at that, I don't. I know that I go 100 this way and I go 30 back. This one is going to have to be 70. Can I delete anything else? What if I deleted this guy?